so this is the second lecture on this course on finite fields. Of course, there are intersections with the course from Peter Moret, and the intersection will keep on growing. And so from yesterday, we consider F a field, and then F a polynomial, which is irreducible. And then we gave a structure to this set, which I'll call the quotient. So the elements are polynomials with coefficients in F and degree smaller or equal than n minus 1, when n is the degree of the initial polynomial. I've been trying to hide from you the word ideal, but Peter reminded us that this is nothing else but the quotient of a ring by an ideal. So there is no life without ideals, so I guess I should have told you since. As one can do by taking quotients of ring from ideals, this has a ring structure, but the ring structure can be given without mentioning the word ideal, except if you don't mention the word ideal, it's a bit more complicated to show that this is actually a ring structure. So the sum of two polynomial expressions of this type is just done component-wise, and when you want to multiply two expressions of this type, you do the product of the polynomials, then you do the division by f, and you take the remainder, which will have the correct degree. Okay? And of course, this ring contains f, and if the polynomial is irreducible, this is a field, which I call stem field, even if Peter teases me, but that's okay. And I refer to f as the stem. Okay? And so sometimes we can indicate, well, I'm just going to follow Peter with the round bracket, this one, so that we forget about this notation. And in f of y, the polynomial f of x, which we can think. So this is a polynomial with coefficient in f. But we can also think of this polynomial as having the coefficients in the larger field, right? So simply because this is contained in this, and so if we take a polynomials with coefficient in this, nobody prohibits us from thinking that this polynomial has coefficients here. So when I think it at coefficients here, then f has y as a root, which is to say that f of y is equal to 0. And actually, one notation which is often used by indicating all this construction is the following. You just write f of y and f of y equal to 0. This is often the notation. So to indicate that you're looking at a field in which the elements are polynomial expressions in y, and the stem is telling you how to make the computation, so dividing by this polynomial. Okay? So this is our construction, and so just to remind, so if you take Q of alpha with alpha squared equal to 2, well, this is nothing else than the field that Peter has indicated with this symbol. right? It's the same notation. It's different notation for the same field. Now I would like also to make a reminder of some names which are often used in field theory. So F1 and F2 are isomorphic. So this means that there is a mapping, call it phi, from F1 to F2. I think so there is this mapping, and this mapping is 1-to-1, so it's bijective, and then respect the operations. Okay, so this is the definition of isomorphism. And so the notion of isomorphisms for fields is a little more subtle than the notion of isomorphisms for groups. Sometimes you have fields that are isomorphic, but they are very different. Okay? For example, if you take subfields of the complex numbers, it can happen that two subfields are isomorphic, but one is real, contains only real numbers, and the other one contains also complex non-real numbers. So the notion of isomorphic is a little more delicate. Then we should remember the notion of subfields. So when a field is contained in another, we say that it's a subfield if they're fields with respect to the same operation, of course, and they share the unit and the zero, right? So this is the notion of subfield that we are going to use. And then the notion of extension, field extension. So the notion of field extension is the following. It's just the data of two fields, E and F, fields such that F is containing E. And sometimes one writes E over F. Well, the reason for which this is emphasized so much is that in this situation, when you have a field inside another field, there's this extra structure of vector space. Okay? If E over F is an extension, then E is also a vector space over F, and so we define the degree nothing else than the dimension of the vector space E over F. This is what we call the degree. And I think the name degree was also used by Peter today, so this is the definition. And so if, you know, in the case that we're interested mostly if E is a finite field, then E over Fp This is the fundamental subfield is a finite dimensional vector space. So if you have a finite dimensional vector space, it's finite dimensional because everything is finite here. And so it means that this is, as a vector space, is isomorphic to a certain finite number of copies of this. And so the number of elements here will be the product of P as many times as the degree. So you have that the cardinality of this finite field is equal to P to a certain power n, where n is the degree. So whenever you receive the question, give me an example of a field with 6 elements, the answer is there is no such a field, because 6 is visibly not a power of a prime. I guess it's a List number which is not a power of a prime. Okay? So whenever we deal with fields, we always deal with examples of this type. Okay? So before we look at the notion of splitting field that was announced to be covered, I would like to remind you the exercises that I suggested for you, and it was to look at the following stem fields. So I wanted, there were 3 or 4, I guess, but I would like to concentrate on the following 2. So if we take the field with 3 elements, and then we add alpha, and the stem is alpha squared equal to 2. Okay? So this is a field, I claim, and in order to prove that this is a field, one has to check that the polynomial x squared, so this is x squared minus 2, right? Which modulo 3 is x squared plus 1. Well, this is irreducible. Well, in the case of a polynomial of degree 3, it's kind of obvious how to prove that this is irreducible, because if it was reducible, it would have a root. And if you check with the 3 numbers 0, 1, and 2, you verify that none of them is a root, so this is irreducible. But, and so you have this field, and this field has 9 elements. Okay? And so the multiplicative group here so I'm looking at the non-zero elements. This is a multiplicative group with 8 elements. Okay, so we'll say something more about these multiplicative groups of finite fields. So the exercise was to write down the multiplication table for this, right? And then there was this other example. So I'm just going to give another name to the generator. And the stem is the following. And again, the polynomial, so the polynomial in this case is x squared plus 2x plus 2 is irreducible. We were hoping that this board would be easier. I think it's the chalk. Okay, so you have 2 elements, 2 fields with the same number of elements, and they don't exactly look the same, right? Because they're done using 2 different stems, right? And furthermore, the role of alpha inside here seems to be very different than the role of beta inside this field, right? For example, if you look at alpha inside this multiplicative group, sorry, here, I guess you can write curly, like round bracket or square brackets is the same. So if you take, so this is an element of a finite group. So an element of a finite group will have an order. The order is the minimum power that you have to take in order to obtain 1. So what is the order of alpha inside this group? So if you square alpha, you get 2. The order of alpha is 4, right? Because alpha power 4 is equal to 2 squared, which is 1. So the order has to be a divisor of 4, but alpha squared is different from 1. Okay? So the order cannot be 2, so it has to be 4. And now if we want to do the same with beta, well, if we make beta squared, this is beta plus 1, and this is definitely not 1. So the order is not 2. But the order has to be a divisor of the group order, right? The group order is 8. So the order of the element can be, it's not 2, it can be 4 or 8, right? But if we take beta to the power of 4, this is the same as beta plus 1 squared, which is beta squared plus 2 beta plus 1. And beta squared is again beta plus 1. And so what do you get? This is 2, which is again not 1. All right? So the order of beta here, what is the order of beta? 8. 8 if you want, just by exclusion, right? It's not 2 and it's not 4. So again, this is another difference between these two fields, right? One is done with a generator which is order 4, and the other one is done with a generator of order 8. So it seems like that, at least in the case of finite fields, two fields can have the same number of elements, but still look very different one from the other. But as a matter of fact, there is a theorem which I will state and prove. So the theorem says the following. If F1 and F2 are finite, then F1 is isomorphic to F2. Well, certainly if they're isomorphic, then they have the same number of elements, right? But this theorem says that this is an if and only if. Okay? So two finite fields are isomorphic if and only if they have the same number of elements. And so in this case, these very differently looking fields, they do have the same number of elements. So F3 of alpha is isomorphic to F3 of alpha, of beta. Okay? And so I guess as a training, hopefully today, we will construct explicitly, using some theory, the isomorphism between these two fields. Okay? And in order to prove this, we would like to develop a bit more theory and explain why this theorem is correct. Okay? So before I prove why this theorem is correct, I would like to mention the so-called Brown formula. Well, at least I'm translating it from Italian. The Brown formula. I think this is a nickname. Okay. So if alpha and beta are elements of any finite field, and P is the characteristics of this finite field, then when you take A plus B power P, this is the same as alpha P plus beta P. Okay? And this only works with the P that it's the characteristic. Okay? So now it's clear why I call this Brown formula, because one has to be careful that it shouldn't use it if this P is different from the characteristics, and you shouldn't use it even with P is equal to 0, right? And the proof is kind of simple. I'm sure many of you have seen this proof. And so what we do, we just proof of the Brown formula. You just write what that is, alpha plus beta to the power P. This can be written by means of the Newton formula. So it is alpha power P. Then there is a certain sum, and then there is a beta power P. And this sum is a certain binomial coefficient. So P choose J. And then here there's alpha to the J, beta to the P minus J. Sorry, I'm going to rewrite it. This is really unreadable. So this is alpha power P plus the sum for J that goes from 1 to P minus 1 of P choose J, alpha to the J, beta to the P minus J, plus beta to the P. Right? This is the Newton formula. And now you notice that P always divides P over J if J is bigger or equal than 1 and strictly smaller than P. Okay? And divides. Sorry. Divides. Yes. And so simply we just write what this is. This is P times P minus 1 dot 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 P minus J plus 1 divided by J factorial. And this happens to be an integer because it has also a combinatorial interpretation. And you see here J factorial is not divisible by P. So in order to get an integer here, you have to simplify J factorial with anything but the first factor. So this is divisible by P. So the binomial coefficient is actually 0 in Fp, which is contained in F. Right? So all these terms are 0, and so you have this formula, the so-called wrong formula. Okay? Now, the wrong formula has very far-reaching consequences. For example, if you take this field F, then you can write always a mapping from F to F. This mapping is called the Frobenius. VP is called Frobenius automorphism. So you take any element here, let's call it x, and you send it to x power p. Okay, and the reason for which this is automorphism means that it's an isomorphism of a field into itself. Automorphisms are really relevant in Galwa theory. So this is certainly an injective mapping. Certainly the product goes into the product and the sum goes into the sum, okay, because of the wrong formula. And certainly being an injective mapping from a finite field into itself, it has to be an isomorphism, okay? And so, phi is an automorphism of the finite field. Okay, and another property called Frobenius, right? Frobenius. And one property of this Frobenius is the following, that if you have phi of an element alpha, this is equal to alpha, if and only if. Okay, I'd like you to think about this. It's very simple, but it's worth thinking about this for a second. So phi of alpha equal to alpha. Well, this means that alpha power p minus alpha is equal to 0, right? Because the Frobenius of alpha is alpha power p, right? And this means that alpha is a root of the polynomial x power p minus x, which is a polynomial with coefficients in the ground field. I remind you that in this case, Fp is a subfield of F, right? And now, there's another remark, which is also extremely simple. So remarks, I'm going to add up remarks till I obtain what I wanted to do. So the remark number 1 is that in a field, a polynomial has at most as many roots as its degree. Okay, so this polynomial here has at most p roots. Okay, and so do you know an example of a polynomial which has more roots than its degree, but coefficients not in a field, right? Because in a field it doesn't happen. So I guess the example is of a ring, okay, and a polynomial, and this polynomial has more roots than its degree. This is a strange example that I'm asking you. But actually, whenever you take a ring which is not a field, you quickly find one. So for example, so this is a counterexample of this. If you take the ring Z mod 8Z, this is definitely not a field. And you take the polynomial x squared minus 1, which has coefficient in this ring. So this polynomial here has 4 roots. Funny. Sorry? Is there a remark? So if you take 1 squared is 1, 3 squared is 1, 5 squared is 1, and 7 squared is 1, right? So there are 4 roots in this polynomial, right? But if you have a field, there are at most 2 roots in a polynomial of degree 2. Another remark, which is not immediately relevant here, but it's a good time. So the polynomial x power p minus x has all distinct roots. Well, how do you check whether a polynomial has distinct roots in general? There's a way which is very efficient. Yes, you compare it with you take the GCD, the greatest common divisor, with its derivative. So a polynomial with coefficient in a field has multiple roots if and only if, when you take the GCD between this polynomial and its derivative, this is not 1. Okay? This is one of the things which is easy to verify. Okay? But in this case, the derivative of the polynomial x power p minus x. So what is this derivative? So don't tell me that it's p x to the power p minus 1, because p is equal to 0, right? So this derivative is minus 1, right? So this polynomial is necessarily co-prime to its derivative, because its derivative doesn't have any factor. Okay? So this polynomial has all its distinct roots. Another remark, which is the last. Oh, sorry, I wanted to keep this regarding Frobenius. So the last remark, I'm going to write it here, is the following, is that for any t in Fp, t power p is equal to t. So t is a root of x power p minus x, right? And I guess this is what we used to call the Fermat-Little theorem, if you want, or also just the observation that this is true for x is equal to 0, and for x different from 0, t to the power of p minus 1 is 1 because it's a non-zero element of a finite group, so you get 1. But whichever way you want to see it, this is always true. Okay? So if we go back to that question, what are the elements which are fixed by Frobenius? Okay? So the elements which are fixed by Frobenius are the roots of that polynomial, but the roots of that polynomial are p, and here are p roots. Okay? So this is only if and only if alpha is in Fp, right? So the fixed elements of the Frobenius are exactly the elements of the ground field, right? But now think at, for example, the mapping that goes from Fp of alpha, sorry, F3 of alpha into F3 of alpha. So I want to look at the Frobenius here. The Frobenius, and this is the stem that I mentioned before, right? Alpha squared is equal to 2, right? So what is the Frobenius in this case? So Frobenius takes any element x and sends any element x into x cubed. So can you describe it a little more precisely? What is the Frobenius in that case? So we have F3 of alpha. I want to go in F3 of alpha. So alpha squared, let's not forget, is 2. Okay? And so every element here, so I'm studying the Frobenius, right? Every element here is a polynomial of degree at most 1 in alpha. So every element here can be written as x plus y alpha. And I want to do the Frobenius, right? So this goes into x plus y alpha cubed. Okay? But we have a wrong formula here, right? So this is equal to x cubed plus y cubed times alpha cubed. But x cubed is x because it's in the ground field. So this is x plus y times alpha cubed. But alpha cubed is alpha squared times alpha. And alpha squared is 2, right? So this is times 2 alpha. Or if you want, this is x minus y alpha. So this is what the Frobenius looks in this case, right? So exercise. Compute the Frobenius when you look at this other field. With this other stem. Okay? So, and just out of curiosity, look at what you get. Okay? But now we want to discuss these important result regarding finite fields, that basically there is only one isomorphism class of finite fields for every order. And so to do that, we need to discuss the notion of splitting field. We need to discuss this notion. So the input would be F field, and F again polynomial, and n is the degree of this polynomial. So the splitting field, so I'm going to give a definition. So a splitting field for F over F is a field so it's a field extension of F with two properties. It has two properties. So the first property is that F splits in this extension. Okay? So it's a field extension of F. So this field extension, we call it FF. It's this extension. So the first property is that there exists alpha 1, alpha n in this field extension such that the polynomial can be written as its leading coefficient, say a, times the product of x minus alpha j. Okay? So in this field extension, there are all the roots of this polynomial. And the second double I, I'm going to write it there. The second property is the following, is that every beta in this splitting field can be written in the form, so beta, this is going to be like a polynomial expression with coefficients a, I1, In of alpha 1 to the j1, alpha n to the jn. I guess I can write this j1, jn, where j1, jn are integers. Well, yeah. Integers. So what do I mean by this? I mean that every other element of this extension is a polynomial expression, possibly with the negative coefficients, but actually it's enough to put n here. Okay, can be written in this form, or in notation that the splitting field can be generated algebraically by alpha 1, alpha n. This is a different way to say the same thing. Okay? So this is the definition of splitting field. It's an extension that contains the root, and it's generated by the root. So every element is a polynomial expression in the root. Okay? So this seems like an abstract definition, but it's very natural. And actually, the splitting fields of polynomials are exactly, in the case of rational numbers, are exactly what we call Galwa extensions. And their automorphism form a group which is called the Galwa group. Okay? But the theorem that we are interested in using is the following theorem. Given any f and any polynomial with coefficient in f, the following things happen. First of all, there exists splitting field. The second property is the following, is that the degree of the splitting field, so this is the dimension of the splitting field over the ground field, well, this is less or equal than the degree of the polynomial factorial. And when you think at n factorial, you think at the group of permutations, which was already mentioned by Peter. And this is exactly where this inequality is coming from. And thirdly, C, any two splitting fields are isomorphic. Any two splitting fields are isomorphic. So I'm not going to prove this. I mean, we may discuss with Peter if this is a theorem on Galwa theory or in finite fields theory. I think it's a theorem in Galwa theory, so he should prove it. But maybe actually I'm almost sure that no one will prove it. But the proof is not very difficult. Is a matter of constructing stem fields one after the other, okay, until you split the polynomial, and it's just a formal construction, and then the proof of the uniqueness is also a formal proof, but I think the proof of this theorem wouldn't really give us much insight, you know, during CIMPA School, but you can look it and learn it without much effort. But now let's take it in our situation. So let's start with this field. We know this very well, okay? And let's start with this polynomial. Okay? Sorry, x power n. Otherwise, if I started with x power p, the roots of that polynomial would all be here already, right? So it wouldn't be very interesting. So let's start with this polynomial. And then we apply that theorem. What it tells, this theorem, it tells us that there is a unique, up to isomorphisms, splitting field. So let's call F the splitting field. Okay? We know that it exists, right? And it's unique in that sense. So about the splitting fields, I want to remark and justify two things. The first thing that I want to remark and justify is the cardinality of the splitting field here is exactly p to the n. And now, you realize how much this is interesting, because this is very interesting because this is telling us that whenever you take a power over prime p, then there's always a field which has that cardinality. Okay? What is the field? The splitting field of this polynomial. Okay? So the consequence of this is already quite dramatic. And the second thing that I would like to remark is that any field with p to the n elements is a splitting field of x power n minus x. So if I justify the second thing, any field is the splitting field of, with p to the n elements as the splitting field of this polynomial. So, for example, if we take our two fields, our two companions, okay, I'm going to finish this tomorrow, but I just want to mention this thing, is that, so if we take f3 of alpha, alpha squared is 2, well, if you believe 2, this is isomorphic to a splitting field, any splitting fields of x, 3 squared minus x, right? But also f3 of beta, where beta squared is equal to 1 plus beta. This is also isomorphic to this splitting field. Okay? So these two are isomorphic. Right? So you realize what number 2 is telling us. It's telling us that whenever you take two fields with the same number of elements, being both of them isomorphic to x power p to the n minus x splitting field, they are isomorphic among each other. So 1 plus 2 so 1 plus 2 imply that if the cardinality of two finite fields is the same, then they are isomorphic. Since they are both isomorphic, so if this is n, these are both isomorphic to the splitting field of x p power n minus x. Okay? So we need to perform these two tasks. Verify that the splitting field has exactly p to the n elements, and that every finite field with p to the n elements is a splitting field. And this is going to give us the uniqueness of finite fields with the same number of elements. So thank you, and let's enjoy lunch.